Next, NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
NASA engineers have re-established communication with the Voyager 1 spacecraft, Earth's most distant emissary, after months of troubleshooting a glitch that had rendered the probe's transmissions unreadable.
Exploring the depths of our universe, NASA's Voyager mission stands out as one of the space agency's most enduring triumphs. For numerous years, the Voyager missions have served as a conduit to the wonders of the cosmos, beaming invaluable data back to Earth. However, Voyager 1 encountered an unexpected shutdown, only to miraculously come back online and transmit an unsettling signal to Earth. Join us as we delve into NASA's alert regarding Voyager 1's astonishing discovery before its temporary hiatus. At the heart of this remarkable journey is a figure not often in the spotlight, Gary Flandro. An aerospace engineer, Flandro played a pivotal role in shaping the trajectory of the Voyager 1 spacecraft. His ingenious ideas and precise calculations were instrumental in the success of the Voyager missions, now enshrined in the annals of space exploration history. In the mid-1960s, during his tenure at NASA's Jet Propulsion Laboratory, JPL, Flandro made a remarkable discovery. He identified an extraordinary alignment of Jupiter, Saturn, Uranus, and Neptune slated for the late 1970s and early 1980s. This celestial alignment, occurring approximately once every 175 years, presented a unique opportunity that Flandro foresaw: the utilization of gravitational assists. This innovative concept involves a spacecraft gaining speed by navigating past planets, thus conserving both time and fuel. Picture it as a slingshot effect in space. As the spacecraft approaches a planet, it falls into its gravitational pull, accelerating as it moves away. By intricately charting this trajectory, engineers can propel spacecraft on extensive journeys with minimal fuel consumption. Recognizing the potential of this rare planetary alignment, Flandro conceived an ambitious plan, the Grand Tour mission. This mission aimed to guide a spacecraft through an extraordinary odyssey across the solar system, utilizing gravitational assists to explore all 4 outer planets. The envisioned trajectory would enable the spacecraft to successively fly by each planet, capturing data and transmitting it back to Earth. Flandro's proposal showcased ingenuity, offering a novel approach that not only promised fresh insights into the outer planets, but also achieved this in significantly less time compared to individual planet-centric missions. The utilization of gravitational assists not only expedited the mission, but also ensured substantial fuel savings, making it feasible with the technology available at that time. However, considerable challenges loomed. Navigating a trajectory to capitalize on gravitational assists from multiple planets demanded meticulous calculations and timing. The slightest error could spell mission failure. Furthermore, the vast distances involved presented hurdles in communication and data transmission. The spacecraft required sophisticated instruments capable of functioning in deep space and transmitting data across billions of miles. Despite these formidable obstacles, Flandro's proposal generated enthusiasm at NASA. The scientific prospects of the Grand Tour proved too compelling to overlook. Yet, constrained by budget limitations and technical impediments, the mission underwent downsizing. Instead of a single spacecraft exploring all 4 planets, NASA launched 2 Voyager probes, Voyager 1 and Voyager 2. The momentous launch of Voyager 1 on September 5, 1977, recorded a historic chapter in human history and the history of space exploration. This event marked the beginning of an extraordinary journey that has propelled spacecraft to the outer planets and beyond. In doing so, it revealed new wonders and solved mysteries within the solar system and the vast expanses of interstellar space. The Voyager program, inspired by Flandro's visionary concepts, used serendipitous planetary alignments using gravitational assistance to embark on a grand tour of exploration. While the notion of gravity assist was not unprecedented, the Voyager missions pioneered the use of this technology to successively visit multiple planets, plan a grand tour of the outer solar system, and visit regions beyond the stars. The meticulous craftsmanship of the Voyager spacecraft came to fruition under the skilled hands of the Jet Propulsion Laboratory, JPL, in California. Taking inspiration from the Mariner spacecraft blueprints, these ships underwent strategic changes and upgrades. Equipped with 11 sophisticated scientific instruments, the spacecraft set out on a mission to reveal the secrets hidden within the planets, moons, rings, magnetic fields, atmospheres, and radiation in our cosmic neighborhood. Yet, there's more to the story. Nestled within these space probes was an extraordinary surprise, a golden record brimming with Earth's sounds and images. It served as a cosmic message in a bottle. The momentous day arrived for Voyager 1's launch at Cape Canaveral Air Force Station in Florida. However, a hiccup surfaced. A technical glitch with the rocket's guidance system led to a nerve-wracking 2-week delay in liftoff. Finally, on September 5, 1977, Voyager 1 gracefully ascended into the sky aboard a Titan III E-Centaur rocket, bidding farewell to Earth. Speed was paramount for Voyager 1. It charted a swifter path compared to its counterpart, Voyager 2, which had taken flight a fortnight earlier. By November 1977, Voyager 1 effortlessly navigated through the asteroid belt. The pivotal moment arrived in April 1978, when Voyager 1 initiated its up-close exploration of Jupiter from an impressive distance of 165 million miles. On March 5, 1979, it executed its closest pass, skimming a mere 217,000 miles above Jupiter's swirling clouds. This monumental feat positioned Voyager 1 as the second spacecraft ever to orbit Jupiter, yet it was the true pioneer, laying bare the hidden treasures concealed within Jupiter's enigmatic depths. During its orbital encounter, Voyager 1 made startling revelations. It uncovered a discrete ethereal ring encircling Jupiter, eluding Earth's telescopic gaze. Composed of fine remnants from the planet's inner moons, weathered by meteoroid impacts, this slender ring, measuring less than 19 miles in thickness, hovered approximately 50,000 miles from Jupiter's core. To heighten the celestial spectacle, Voyager 1 also chanced upon 2 nascent moons within this ring, Thebe and Metis, both diminutive and peculiarly shaped. Adding to the cosmic intrigue, Voyager 1 shed light on Jupiter's fiery moon Io, exposing yet another extraordinary discovery. Jupiter, renowned as the largest planet in our solar system, boasts an impressive array of moons, with 79 identified satellites to date. Some of these moons orbit closely within the grandeur of Jupiter's rings. However, the most notable are the 4 illustrious Galilean moons, Io, Europa, Ganymede, and Callisto, aptly named after the renowned astronomer Galileo, who first observed them in 1610. Embarking on a cosmic journey towards Jupiter would lead you through its dazzling rings, culminating in a rendezvous with the quartet of Galilean moons, Io, Europa, Ganymede, and Callisto. These lunar giants stand as celestial marvels, each holding distinctive traits and harboring mysteries awaiting exploration. Io, the closest of the Galilean moons, engages in a graceful waltz with Jupiter, maintaining a proximity of nearly 350,000 kilometers above the swirling clouds of the gas giant. To an onlooker positioned on Io's surface, the dominating presence of Jupiter would render it an awe-inspiring spectacle, appearing a staggering 39 times larger than our moon. However, Io's intimate connection with its colossal celestial companion comes with a caveat. Its orbital trajectory is a peculiar dance, completing a full revolution around Jupiter in a mere 42.5 hours, a striking departure from the monthly orbit of Earth's moon. What adds an extra layer of fascination to Io's orbital dynamics is its synchronization with neighboring moons, a captivating phenomenon referred to as orbital resonance. For each orbit completed by Europa, Io manages 2, and for every orbit of Ganymede, it accomplishes 4. This intricate gravitational interplay amplifies the uniqueness of Io's orbit, subjecting it to potent tidal forces that act as a primary catalyst for the Moon's captivating geological activity. As Voyager 1 soared past Io, approaching as close as a mere 2,000 kilometers away, it captured breathtaking images of the Moon's surface. What unfolded was truly extraordinary, a landscape alive with vibrant colors, devoid of any crater marks. The revelations included towering mountains rivaling the height of Everest, expansive volcanic pits stretching hundreds of kilometers, and extensive lava cascading across the terrain. A particularly striking find was the presence of plumes erupting from Io's surface, marking a groundbreaking observation and solidifying Io as the first and only location, apart from Earth, with visible volcanic activity. In addition to these revelations, Voyager 1 confirmed that Io's surface is adorned with various sulfur frosts, casting a captivating array of hues. Notably, Io exhibits a remarkable absence of typical volcanic calderas. Instead, the primary sources of volcanic activity are large lava lakes enclosed by steep walls. Loki, the largest volcanic depression on Io, spanning 200 kilometers in diameter, stands out among these features. These lava lakes, often concealed by a thin crust, are directly connected to subsurface lava reservoirs. Loki, in particular, emerges as a dynamic entity, significantly contributing to Io's heat output. While it typically generates a quarter of the planet's heat, occasional collapses in the crust on its lava lake result in a tenfold increase in heat production. These phenomena underscore the dynamic and captivating nature of Io, a celestial body shaped by the formidable forces of volcanic activity within the vastness of space. Revealing the enigmas of the gas giants, Voyager 1 encountered Jupiter's formidable radiation belts, a consequence of the planet's robust magnetic field interacting with solar winds. Within these belts, energetic particles abound, posing potential hazards to spacecraft and upcoming missions. Additionally, Voyager 1 observed lightning and auroras in Jupiter's atmosphere, accompanied by radio emissions that vary with the planet's rotation. These emissions stem from electrons spiraling along magnetic field lines, interacting with plasma within Jupiter's magnetosphere. The spacecraft unveiled Europa's smooth, icy surface, suggesting a geologically youthful interior concealing a potential hidden ocean of liquid water. Ganymede, on the other hand, boasts its own magnetic field nestled within Jupiter's magnetosphere. Callisto, with its heavily cratered surface, indicates a comparatively quiescent geological history. Lastly, Amalthea exhibited a long reddish appearance, likely influenced by sulfur from Io after departing from Jupiter. Embarking on its celestial journey, Voyager 1 set a course for Saturn, its next cosmic destination. On November 12, 1980, the spacecraft approached Saturn's vicinity, gracefully passing the planet at a distance of around 77,000 miles or 124,000 kilometers. During this voyage, Voyager 1 also conducted a close flyby of Titan, Saturn's largest moon, getting as near as approximately 430 miles or 6,490 kilometers. This close encounter marked the inaugural exploration of Titan's dense atmosphere by a spacecraft. While Pioneer 11 had previously visited Saturn, Voyager 1 pioneered the unraveling of many of the planet's mysteries. Hurtling past Saturn within about 77,000 miles from the top of its clouds, Voyager 1 made a multitude of discoveries and observations that reshaped our understanding of Saturn and its assortment of moons. Among the most enthralling revelations was the presence of a previously undisclosed ring encircling Saturn, later named the G-ring. This ring, unseen from Earth, comprises minuscule particles likely ejected from Saturn's inner moons due to collisions with meteoroids. The G-ring, exceptionally faint and narrow, spans approximately 4,700 miles or 7,500 kilometers in width, with its inner edge situated around 104,000 miles or 167,000 kilometers from Saturn's center. Furthermore, Voyager 1's acute observations identified 5 newly discovered moons frolicking within or near Saturn's rings: Prometheus, Pandora, Atlas, Epimetheus, and Janus. These cosmic companions contribute to the diversity of Saturn's assembly, enhancing our comprehension of the planet's intricate system. These moons, characterized by their modest size and irregular shapes, range from approximately 40 miles or 64 kilometers to 90 miles or 144 kilometers in diameter. They are sometimes referred to as shepherd moons because of their pivotal role in maintaining the shape and stability of Saturn's rings through their gravitational influence. Among Voyager 1's significant findings was its exploration of the intricate dynamics of Saturn's rings. Composed of numerous icy and rocky fragments spanning from minute specks to sizable boulders, these rings exhibit a complex structure. Contrary to being smooth and uniform, Voyager 1 revealed that the rings contain gaps, undulations, contortions, and twists. These formations result from interactions between the ring particles and Saturn's moons. For instance, Voyager 1 observed a gap in the A-ring attributed to gravitational interactions with the moon Mimas. It also detected a rippling pattern in the B-ring influenced by the gravitational pull from the moon Janus. Additionally, peculiar spokes were observed in the B-ring, temporary streaks possibly caused by electrically charged particles within Saturn's atmosphere. Furthermore, Voyager 1 conducted measurements of Saturn's magnetic field and its magnetosphere, the expansive region of space influenced by the planet's magnetic field. This magnetic field, akin to Earth's but stronger and tilted, is generated by Saturn's rotation and its interaction with the solar wind. Extending well beyond its rings, Saturn's magnetosphere forms a vast protective bubble around the planet. Throughout its exploration of Saturn's domain, Voyager 1 encountered a plethora of celestial phenomena. It identified plasma particles emanating from Saturn's atmosphere, rings and moons, in addition to capturing the beauty of auroras and radio emissions. Moreover, Voyager 1 closely observed several of Saturn's moons, including Titan, Enceladus, Mimas, and others. Notably, it discovered that Titan possesses a thick atmosphere composed of nitrogen and methane, distinguishing it among the moons of the solar system. Enceladus displayed a smooth, bright surface with minimal craters, suggesting geological activity and a potential subsurface ocean. Mimas showcased a vast crater named Herschel, covering a third of its diameter, while Iapetus revealed a striking contrast between its dark and bright hemispheres. On February 17, 1998, Voyager 1 surpassed NASA's Pioneer 10 as the farthest human-made object from Earth. By August 16, 2006, it reached a distance of 100 astronomical units from the Sun, a significant milestone that marked its entry into interstellar space. Voyager 1 etched its name in history as the first human-made object to achieve this feat. Despite its considerable distance and age, Voyager 1 continues to maintain communication with Earth through the Deep Space Network, DSN. The Deep Space Network, commonly known as the DSN, is more than just a communication system. It stands as a scientific powerhouse situated at NASA's Jet Propulsion Laboratory. Operating radio antennas positioned at 3 locations globally, Australia, Spain, and California, the DSN strategically places these sites at nearly equal distances from one another to maintain continuous contact with spacecraft, accommodating the Earth's rotation. The roots of the DSN trace back to 1958, when JPL established portable radio tracking stations in California, Nigeria, and Singapore to guide Explorer 1, America's inaugural artificial satellite, during its groundbreaking orbit around Earth. The formal establishment of the DSN took place in December 1963, with subsequent construction and ongoing upgrades to its radio antennas over the years. Throughout its extensive history, the DSN has played pivotal roles in space exploration, steering satellites into orbits around distant planets, safely landing spacecraft on asteroids, and broadcasting iconic moments such as Neil Armstrong's historic moonwalk. In its communication with spacecraft, the DSN utilizes 3 categories of antennas with varying sizes. The largest antennas, spanning 70 meters, are essential for establishing communication with distant objects like Voyager 1, currently exploring the outer reaches of our solar system. These massive dishes play a crucial role in compensating for the remarkably weak signals emitted by spacecraft, signals that weaken significantly over vast distances. The precision of these antennas is nothing short of remarkable. They must maintain flawless accuracy to within a single centimeter to ensure optimal reception of signals. Additionally, each site incorporates antennas of 34 meters and 26 meters in diameter, designed for tracking both distant and Earth-orbiting spacecraft. Despite their advanced technology, the DSN antennas encounter the challenge of amplifying faint signals while minimizing background noise, including radio static emitted by celestial objects throughout the universe. Astronomers employ ingenious methods to decipher signals, effectively separating satellite transmissions from background noise. Furthermore, they must address equipment-generated noise, particularly infrared radiation or heat. To counteract this, amplifiers are cooled to extremely low temperatures, just a few degrees above absolute zero, preventing heat interference with sensors. The DSN employs a highly effective technique known as arraying, utilizing multiple antennas to capture signals from the same source. This approach is particularly advantageous for radio waves, characterized by long wavelengths and less susceptibility to atmospheric interference. By combining these strategies, the DSN adeptly locates and tracks spacecraft, even those that have ceased transmitting signals, functioning akin to a massive radar system. Impressively, it successfully pinpointed India's Chandrayaan-1, currently in orbit around the Moon. However, the DSN's capabilities go beyond spacecraft tracking and communication. It also plays a vital role in scientific research. Collaborating with various spacecraft missions, it assists in collecting valuable data for scientific exploration. The DSN is not merely a messenger. It also serves as a detective, capable of unveiling secrets concealed within the signals it receives. During a mission, the DSN proved instrumental in making a groundbreaking discovery: the presence of a hidden ocean beneath the icy surface of Enceladus. As Cassini sped past Enceladus, its velocity experienced fluctuations due to variations in gravitational pull caused by different materials beneath the Moon's surface. These alterations impacted the frequency of Cassini's transmissions, which the DSN keenly detected. Through a thorough analysis of these frequency shifts, astronomers inferred the existence of an underground ocean. Yet, the DSN's investigative prowess didn't stop there. It also delved into the enigmas surrounding Saturn's rings. In tandem with Cassini in 2005, it conducted its initial radio occultation observations, transmitting signals from behind the rings back to Earth. As these signals traversed the rings, their strength fluctuated based on the density of the ring particles. Utilizing 3 distinct radio frequencies simultaneously, each affected differently by particle sizes, astronomers obtained intricate profiles of the ring's density and composition. Nevertheless, the DSN isn't confined to a supporting role. Through a technique known as radar astronomy, it has the capability to directly image objects such as asteroids by bouncing signals off them. In a captivating demonstration of Einstein's theory of general relativity, the DSN transmitted radio signals to the Viking spacecraft while Mars and Earth were positioned on opposite sides of the Sun. This experiment unveiled gravitational time dilation, illustrating that light bends around massive objects, resulting in delays in its journey. Now, let's delve into today's pick from our subscribers. Inside NASA's control center, an air of urgency pervaded as scientists and engineers gathered around monitors displaying data from Voyager 1. Whispers of excitement and anticipation filled the room as they eagerly awaited the latest transmission from the spacecraft hurtling through the cosmos. Suddenly, the screens burst to life, and a wave of surprise swept over the room. Voyager 1 had made a discovery that challenged all known laws of physics. It had entered a realm where the fabric of space-time appeared to warp and twist in ways previously deemed impossible. The team of scientists exchanged incredulous looks, grappling to comprehend the implications of Voyager 1's groundbreaking discovery. However, before they could delve deeper into the mystery, a message flashed on the main screen. NASA issued a warning that Voyager 1 had made an impossible discovery before initiating shutdown. Confusion and frustration rippled through the room as the scientists grappled with the sudden directive to cease communication with the spacecraft. Unanswered questions hung in the air, leaving the team in a state of bewilderment. Dr. Emily Hayes, the lead scientist on the Voyager 1 mission, stepped forward, her voice resolute despite the tumult swirling around her. "We must adhere to NASA's directives," she affirmed, "but we cannot turn a blind eye to this discovery. We must persist in seeking answers, even if it means deviating from protocol." However, as days transformed into weeks and weeks into months, the enigma surrounding Voyager 1's revelation remained unresolved. Nevertheless, the recollection of that pivotal day endured, igniting the team's resolve to unveil the universe's hidden secrets. Navigating the challenges of interstellar communication, the exchange of information between Voyager 1 and Earth is not instantaneous. It is subject to time delays based on their distance apart. Radio signals, moving at the speed of light, require approximately 21 hours to traverse the vast distance between Voyager 1 and Earth, creating a lag in communication. When NASA transmits a command to Voyager 1, a 21-hour wait ensues for confirmation that the command has been executed. Similarly, when Voyager 1 transmits data or images to Earth, it takes 21 hours for NASA to receive them. This communication isn't continuous. It is contingent on various factors such as power availability, data rate, antenna precision, and interference from external sources. Voyager 1 operates with limited power generated by its radioisotope thermoelectric generators, RTGs, which diminish over time. Consequently, decisions must be made regarding the utilization of instruments and systems at any given moment. Additionally, as Voyager 1 distances itself from Earth, its data rate diminishes due to a decrease in signal strength. The slightest deviation from the optimal antenna direction can result in signal loss. Despite these hurdles, Voyager 1 persists in relaying valuable data and images to Earth through its radio communication system and the Deep Space Network, DSN. It consistently receives commands and updates from Earth to ensure its proper functioning. This ongoing communication between Voyager 1 and Earth stands as a remarkable testament to human ingenuity and curiosity. Moreover, it highlights the enduring partnership between Voyager 1 and NASA, spanning more than 4 decades. Yet, what unfolds for Voyager 1 in the vast expanse of interstellar space? Interstellar space, situated between stars within a galaxy, is not a void. Rather, it teems with diverse forms of matter and energy, including gas, dust, cosmic rays, neutrinos, photons, and dark matter. While components in interstellar space are sparse, it resembles a near-perfect vacuum due to their widely dispersed nature. One way to delineate the boundary of interstellar space is by observing how the Sun and other stars influence their surroundings. The Sun emits a continuous stream of charged particles and magnetic fields known as the solar wind. This emission creates an expansive bubble around our solar system referred to as the heliosphere. The term heliosphere is derived from the Greek word helios, meaning the sun. The formation of the heliosphere, the protective bubble around the Sun, is a gradual process taking over 1,000 years to develop. The concept of the heliosphere took root around 1955, credited to physicist Leverett Davis. Early scientists associated the presence of cosmic rays with the heliosphere. In 1955, what we now know as the solar wind was termed solar corpuscular radiation, identified as a crucial element of the heliosphere. In simpler terms, the proposal suggested that solar corpuscular radiation generates a growing bubble, gradually enveloping our solar system. This expanding bubble is what we refer to as the heliosphere. Certain conditions could impede this process, such as pressure from the interstellar medium, the material found between stars. According to NASA, the formation of the heliosphere is a consequence of the magnetic field produced by the solar wind. After the Sun releases the solar wind, a continuous stream of charged particles, it travels beyond all 8 planets, extending roughly 3 times the distance to Pluto. Ultimately, it encounters the interstellar medium, leading to the phenomenon known as the termination shock. Heliospheric exploration has been underway for numerous decades, with researchers, physicists, and scientific organizations working to unveil the precise structure of the solar system's heliosphere. Intriguingly, the heliosphere doesn't adopt a perfect sphere. Its shape and dimensions are in constant flux due to the dynamic interplay of the solar wind and the interstellar medium. The heliosphere's form and size hinge on 3 primary factors: the overall movement of the heliosphere and the Sun, the solar wind, and the interstellar medium. The latter 2 exhibit particularly fluid characteristics, a momentous achievement and a lasting legacy. Voyager 1 embarked on a significant mission to explore interstellar space and unravel its mysteries. However, determining the precise moment it crossed the heliopause, the boundary between our solar system and interstellar space, posed a considerable challenge. There were no explicit signs or signals indicating, "Hey, you're in interstellar space now." Consequently, Voyager 1 relied on its reliable instruments to gather clues. It diligently measured various parameters, such as the density of plasma, the strength and orientation of magnetic fields, the intensity of cosmic rays, and even detected plasma waves. The initial indication that Voyager 1 was nearing interstellar space emerged in May 2012. A sudden surge in cosmic rays, those swiftly moving particles originating from outside our solar system, caught its attention. This surge hinted that Voyager 1 was departing from the protective confines of the heliosphere and entering a region where cosmic rays were more prevalent. It was akin to stepping into an entirely new frontier of space. In June 2012, Voyager 1 encountered another significant piece of evidence. It observed a decrease in the quantity of particles from the solar wind, indicating a departure from the source of these particles, the Sun. However, relying solely on this clue wasn't sufficient to conclusively state that it had reached interstellar space. Various factors could account for the change in solar wind. The conclusive confirmation emerged in August 2012, when Voyager 1 identified a substantial shift in plasma density and the orientation of magnetic fields. Plasma, a gas composed of charged particles capable of generating magnetic fields and carrying electric currents, played a crucial role. The spacecraft utilized its specialized instrument, the Plasma Wave Instrument, PWS, to measure plasma density. This instrument detected vibrations in plasma caused by different events in space. On August 25, 2012, Voyager 1's readings displayed a sharp increase in plasma density, soaring from approximately 0.002 particles per cubic cm to around 0.08 particles per cubic cm. This surge signified that Voyager 1 had entered a region where plasma was significantly denser than within the heliosphere, conclusively affirming its transition into interstellar space. It was akin to navigating from a serene river into the tumultuous expanse of space. On August 25, 2012, Voyager 1 continued its celestial journey by scrutinizing the strength and orientation of magnetic fields using its reliable magnetometer, affectionately known as MAG. This instrument possesses the ability to detect alterations in magnetic fields caused by electric currents or mobile charges. During this meticulous examination, Voyager 1 registered a shift in the magnetic field's direction, amounting to approximately 20 degrees. This alteration signaled that Voyager 1 had entered a realm where the magnetic fields were arranged differently compared to those within the heliosphere. The combination of these magnetic field measurements and earlier revelations regarding plasma density served as compelling evidence that Voyager 1 had indeed crossed into interstellar space, marking an extraordinary milestone in the annals of space exploration. However, immediate confirmation of this groundbreaking discovery was hindered by Voyager 1's considerable distance from Earth. The transmission of its signals took some time to reach us. Additionally, scientists devoted several months to the careful scrutiny and validation of Voyager 1's data before officially disclosing the revelation to the public in September 2013. This meticulous process underscored the significance of thorough scientific inquiry in the realm of space exploration. Nevertheless, the ongoing communication with Voyager 1 is not an everlasting prospect. The primary factor behind this limitation is the finite nature of Voyager 1's fuel, and eventually it will exhaust its power, navigating aimlessly through the vastness of the galaxy. According to NASA's projections, Voyager 1's available power is anticipated to sustain the operation of a single instrument until the year 2025. Beyond that point, the spacecraft will be compelled to cease its radio transmissions, ushering in a perpetual silence. Despite this impending radio silence, Voyager 1 will persist in its odyssey through interstellar space. Encapsulated within its structure is a golden record, a repository of sounds and images representing Earth, a poignant message intended for any potential extraterrestrial entities it might encounter. Beyond its role as a cosmic messenger, Voyager 1 will stand as an enduring symbol of human curiosity, creativity, and ingenuity, etching its legacy into the cosmic expanse for eternity. Thank you for joining us on this cosmic journey. If you enjoyed this video and want to explore more fascinating topics about space, science, and the wonders of the universe, make sure to hit that subscribe button and ring the notification bell. Don't miss out on our upcoming content. If you have any questions, thoughts, or topics you'd like us to cover in future videos, feel free to leave a comment down below. Your feedback is invaluable to us. Remember, the universe is full of mysteries waiting to be unraveled, and we're thrilled to have you on this cosmic exploration. Until next time, keep looking up, stay curious, and keep reaching for the stars. See you in the next video.